And we're back. Was anybody supposed to remind me of anything?
You gotta get here sooner.
Yeah, I know. I never had problems parking here this time. I always have tons of open spots in the back of the lot by the lake. But there's like no spots today.
Like 10 o'clock, it's always pretty bad.
Not in the back of the lot by the lake. I mean, I always have a choice of 15 spots. As long as I'm willing to park in the back of that lot.
It's not that.
I haven't had a problem until today.
Neither have I. I was here at like.
So you can vouch that I'm not lying.
Yeah, I was.
The lots are packed today.
It was full by like 9.
There's something going on in campus, I think. Okay, so last time we were still talking about I/O stuff. What were we talking about right at the end of class last time? Look at your notes. I think we were talking about CPU speeds and comparing CPUs to each other and the architecture of them and multiple cores. Is that correct? Okay. So now let's kind of think about how all that connects to memory. So back here are several slides. I think we had kind of a picture. That's not it. We had a picture of our computer, right? So we have all this crap, and one of those things is the CPU. Okay? So the CPU is something we talked about last time. Then we have our disk controllers, things that handle our hard drives and things like that. And we spent a day last week talking about mechanical hard drives versus solid state. Is that correct?
Yes.
Sound accurate? Okay. Last time we were talking about I/O devices, keyboards, printers, mouse, that kind of stuff. Monitor, I don't think we talked too much about graphics adapters, but bottom line is, well, I'm sure we'll get off on a tangent related to it at some point, but bottom line is we have this other thing that displays crap to the screen, which is our main way of viewing the computer, correct? Fine. So this would be involved in the I/O world as well. So this will be the output side of things. Sometimes we're outputting to a hard drive, sometimes we're outputting to an external hard drive or an external device, sometimes we're outputting to a monitor, which flows through the graphics card. Right? But at the core of all of this, we have our memory, our RAM. Okay? Now, how does RAM work? I think we were talking about, was that this class or architecture when you were talking about memory with the big numbers? I think architecture, right? The hexadecimal?
Sure, yeah.
Yeah, pretty sure. You guys are supposed to be able to keep the classes apart. I can't. All right, so tell me what you know about memory. What is memory? We know how much we have, right? We get our laptop, get our desktop. They come with 4 gigs of RAM. We come with 8 gigs of RAM, something like that. We can upgrade it to more RAM than that. Okay. Well, what is memory? What does more memory let us do? As opposed to more hard drive space. What does more memory let us do?
Quicker access.
Okay, tell me about that.
You don't have to.
And actually, I want to leave that chart up. I know
The RAM allows the computer to store things quickly and access quickly.
Okay, what kinds of things do we store in RAM? Yeah, you're definitely a key word there is the quickly part. Okay, that's an important aspect of RAM. It's fast, really fast. Okay, what kinds of things do we store in RAM? As opposed to what kinds of things do we store on a hard drive? So regardless of what technology our hard drive is using, it's an I/O device, it's an output. Well, it's I/O device, input and output, right? We read from the hard drive, we write to the hard drive. And regardless of what kind of technology that drive's using, is it connected through USB? Is it connected through FireWire? Is it connected through serial ATA, either external or internal? Whatever it's connected by, its job is to store crap, right? And we need to be able to write stuff to it and read stuff from it. What kinds of things do we store on the hard drive?
Programs.
Programs. What about the operating system? Is the operating system stored in the hard drive? Yeah, how many of you have ever installed an operating system, installed Windows and the Mac OS or Linux, as opposed to getting a computer that already has it on there? How many of you have never installed an operating system, just out of curiosity? How many of you are lying? Okay, so usually when you install the OS, part of the installation process, it asks you what disk do you want to install to, right? Gives you your options, which disks are installable. Sometimes it won't let you install to an external device for whatever reason. But whatever it is, you're going to pick a hard drive, one of the hard drives, and that's where that operating system, which at its core is an application program, right? It just happens to be the application program that launches other application programs. So think of your operating system as kind of like your main method in a program. Everything begins and ends with main, right? When you start running a computer program, you start off in main, and whatever main says to do, it goes and does it. So when your operating system starts up, it's just in this constant loop of waiting for user interaction, right? You click on something, something happens. It's an event-driven thing. So when we talk about our more modern operating systems that allow multi-programming, which allows more than one program to run at once, the multitasking type stuff, when we think about that stuff, everything's event-driven. If we click on one program versus another, what happens to that program? It becomes the foreground, right? That is an event. A click is an event. A button push is an event. Okay, so most of our modern operating systems are event-driven. They respond to I/O events, just like we talked the last time about our CPU responds to events. Our CPU either eats through code, think of it like Pac-Man, right? Okay, either eats through code or pauses because sometimes you need to throw something back on the grill, right? Pac-Man can't eat something yet because it's still cooking. So we throw it out of the line, and we'll throw it back in the end of the line because Pac-Man's just a glutton. CPU just keeps biting. But our hard drives store our operating system, which is just one big program, kind of the mother of all programs, okay? It stores our other application programs, Microsoft Word, Office, pick it. Your PC video games. If we're thinking about hard drives on your Xbox or your PlayStation, you have a hard drive built into it. I don't even know what the hard drive size is on the PS4. I know the PS3, I think, shipped with an 80 and a 160 gig hard drive or something like that. You could upgrade it with an external one if you wanted to, but the hard drives of the new machines, I'm guessing, are bigger. Maybe they're 1 terabyte. Anybody happen to know? 500 gigs for a PS4? Okay. So that's your amount of storage space you have to download games. So when you go on there, not just games, but also other content, things like that. Apps. Now everything has apps on it, right? So when you download those, they're getting stored on the hard drive. So hard drives are for long-term storage. Make sense? What kind of stuff do we store in memory, in RAM? Okay, she said it's fast. So probably stuff we need to access fast. We wouldn't want to store things on the hard drives that we need to access fast. Now, one observation we might make is that the size of hard drives tend to be substantially larger than the size of RAM. You buy a new hard drive, or you buy a new computer today, maybe it has a 1 terabyte hard drive, and it has 8 gigabytes of RAM, right? Kind of disproportional. But they also are disproportional when it comes to speed. Now, you mentioned temporary stuff, right? So RAM is for temporary storage, where hard drives are for long-term storage. When our computer first loads, when it launches, and that BIOS, that little beginning program that has like the text on the screen or whatever, that's the thing that actually does what's called bootstrapping, where it connects all your stuff together and loads the initial program. Okay, that gets Windows loading. All right, you get the little thing that says starting Windows, and you finally get your first graphical thing, right? The Mac, you don't see the text; it just shows the bare white screen with the Apple logo in the middle. The text is there; it's behind the scenes. You may have seen it if any of you have iPhones. Sometimes when something quirky happens, you'll see the, bunch of Unix-like text lines, and that usually means something bad has happened and you have to reinstall the OS, right? So it's not that the Mac and the PC are any different; just Apple loads the picture earlier. Okay. So, in any case, RAM is where the hard drive, the BIOS, is saying, take our operating system from the hard drive. Don't remove it from the hard drive, but copy it. Copy the executable aspects of it, the current stuff we need from it. Copy it into RAM, memory. Okay? Because we need to operate out of that in real time when we're running our computer. And we want to operate out of RAM rather than hard drive because RAM is fast. We don't like sluggishness. Okay, something we're going to eventually talk about in here when we talk about the details of memory management is virtual memory. What's virtual memory? How many of you have heard of virtual memory? Most of us have probably heard of it. What is it?
It's basically memory on your hard drive.
Using a portion of your hard drive to fake memory. So when you have a computer that didn't come with enough RAM, or you have too much stuff you're running your computer, and you don't have enough RAM to support the stuff, we have this thing called virtual memory, which allows us to fake like we have more RAM. It just happens to be that a portion of our RAM is incredibly slow. So part of the job of the memory manager is to make sure when we're actually using something, when we click on a program that we want in the foreground, that the short-term memory associated with that program leaves virtual memory and somehow gets into real memory. So there might be a slight delay at first as we're swapping things out between virtual memory and real memory. But ultimately, when we're using the program, we want to be operating out of RAM, real memory, because it's fast. Okay? Now, when we think about our computer programs, every time we create a variable, is that getting created on the hard drive or created in RAM? When we say int I equals 5, is that creating a little spot on your hard drive to hold a variable named I and setting it equal to 5? Or is that creating it in RAM? Or is it both? Which of those options? Just RAM? Not both? Okay, why not? Why wouldn't we put it on the hard drive?
Because it's likely that you're not saving it long term.
For variable definition, it's beyond likely, right? Beyond likely. It's a very temporary thing. When we create a loop in Java and we say int I equals 0, that variable doesn't even live throughout our entire program. It just lived for the extent of the for loop, right? So these are very, very, very short-term type things. Now inside your program, if you decide you want to store something long-term, we can then turn around and we can write it to disk. We can choose, for instance, we've displayed stuff to the screen. So that's one of our I/O type of behaviors with that we use with Java. We say system.out.println, okay, and that will interrupt the CPU, the runtime of it. Say, display this crap somehow, whatever the Java magic behind the scenes is. Display it somehow out to the screen. Make sense? Okay? That will trigger an interrupt. Because the CPU is super, 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 super fast. Make sure you get enough supers in your notes. I think there was 8, but I'm not sure. Okay? Very fast. Was it? First couple I mumbled.
Yeah.
Super, 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 super. It was 8. I guarantee I recreated that perfectly.
See, but then we created that perfectly. That was 7.
Huh?
Pretty sure you just did 7.
No, it was 8. Zero indexed.
Stop the recording, go back.
That'll be an exercise for the reader.
Doesn't
Okay.
indexing mean that you're back at 6?
Huh? No, it means the first one I counted was 0.
Right. Then you'd have 6.
No, I have 8. You counted 7, but you started with 1. So you don't know how to count right, is what I'm
If I
saying.
started at 0, then I'd be at 6.
No, that means you counted wrong. I mean, these courses have a prerequisite. I didn't think we had to offer the prerequisite of numbers. No numbers. Professor's always right. Ask my wife. or many, 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 many other things.
So it's always right with exceptions.
Almost all exceptions. to be very honest. I brought in the garbage can in the mail without being told yesterday. It was a big win.
Progress.
Any of you married in here? You know exactly what I'm saying. It was literally a big win. I'm not exaggerating with that. That's brownie points. I'm going to rely on that as an excuse next time I forget. Oh yeah, then when I grilled dinner, I forgot to lock our grills in the front, so I go out our front door and I forgot to lock the door. And then I got yelled at that I remembered to turn the grill off, which I totally did. But my mind was on the steak, not locking the door when I was coming back in. It was,
Priorities.
yeah, very short-term memory loss. All right, so memory has to be very, very fast. When we're creating our variables, often in our programs, those variables only live for a very tiny short period of time. Correct? Whereas maybe in a bigger program, they might last longer, but they're still only going to last for the length of the program. And most of the programs we write, we hit the little play button and the program runs, and how long does the entire run of the program take? A fraction of a second, right? Sometimes we've inserted some I.O. though. Please enter a number between 1 and 10. How long does the program take to run then? Longer, right? Depends how quickly we enter a number in. But any way we cut it, it's probably going to be longer because chances are we're not going to be able to move our finger, push a button, then press enter nearly as fast as that CPU could have just processed a program without I.O. Correct? We're not that quick. Okay, so it'll take longer. Now, what's the longest running program any of you have ever written? One with an infinite loop. And how long did you let it run for? Remember the fraction assignment you guys probably had in 250? We were dealing with adding fractions and the greatest common divisor problem before we actually used the Euclidean algorithm. Became a time complexity problem. Remember that? Where if we were adding a bunch of fractions, we were constantly reducing those fractions. It took a very, very long time. And I think in class we brought that example up. We were talking about time complexity. We brought the example up and I think we let it run for 4 or 5 minutes and then finally just gave up on it, right? Well, you could write that program. It could take days. Would it eventually give you an answer? Yeah, eventually would. As long as you didn't get bigger than the size of integer or something like that for your numerator denominator. But if you used big integer, which allows you to have an arbitrary size number, if you use that, but didn't use the greatest common divisor, Euclidean algorithm, you just wrote your own crappy one, that functionally was correct, but was horrifically inefficient. You just basically started at 1 and, or started at 2. Does this evenly divide it? Does this evenly divide it? Probably start at the top one and go down. But, you potentially check every single number, even though you don't have to check a whole bunch of them. You could have a program that could take days or weeks to run. Are there programs designed to run for an arbitrary amount of time? Servers. What do we mean when we say the word server? Server kind of has 2 meanings, right? When you hear server, one thing you might think of is a physical computer. Probably something really awesome looking. Your normal computers are like a laptop size thing, or your even a desktop, or something like that. When you think server, like if you imagine what the server room here on campus looks like, where all of our, where the cuw.edu server lives, that guy. We probably imagine it being kind of an expensive big computer because it has bigger stuff in it, more stuff in it, right? To do server stuff, right? That might be one idea we have associated with servers. And that's correct.
A laptop here?
Huh?
You mean the server here at Concordia is not a laptop?
Okay, well that's one correct perception, is that it's a physical piece of equipment. Okay, we can call that a server. For instance, that Mac Pro we have down the hall there, we can certainly call that a server. It's built to be that type of thing. Okay? What else? How else could we think of a server? We could think of it as a piece of software. It's a piece of software that serves information. It responds to requests. So for instance, one program that we have running here on campus, and that Google has running at their office, and every other website you've ever gone to, their business has it running, is a web server. That's a computer program that responds to HTTP requests. HTTP, Hypertext Transport Protocol, is just a bunch of formatted strings. You know, you say get this page, index.html, and it responds to that proper language, the proper HTTP request language, with the actual contents of that site. So for example, if I come out here, oh, I don't know where that's going. Tell us what you think, text box. So let's telnet to Google, let's do cuw.edu. So telnet is a program that allows us to remote into another computer. So we're opening up a socket. We're essentially recreating what your web browser does, but we're doing it at command line so we see it. But I want to telnet to port 80. I think this is the right format. It might be :80. We're about to find out. Okay, so we're connected to cuw.edu. Now I happen to know that the default web page on most servers is called index.html. So when you type in www.cuw.edu, it's going to give you, by default, the page index.html. It might also give you index.htm. It might also give you index.php. Depends how they have their server set up, but most sites, it'll be index.html. So I'm going to type get index.html. I'm going to press enter. I might be doing it wrong. Let me. Keep killing me. Nothing to see here. Just in case that wasn't where the web server was running, I suspect it was. Telnet www.cuw.edu. That's definitely where the web server is running. Port 80. Connected there. Might require capitalization. Okay, well, we got a response. So index.html did not exist. So let's try get index.htm. Also didn't exist. Here, just so we get the guess right. Here's the site. Index.html. Okay, well that popped up right. Let's try this. Get home.htm. Get home.html. Since we can't figure out Concordias, we'll go to Google. All right, so the document moved to here. So they, anyways, you see HTML come back from that, right? So this is just if we go to index.html, it's telling us the document has moved to another site, which is probably index.htm or something else. Whatever, doesn't matter. Point is, we just talked to Google's web server. We used a very rudimentary command, the get command, which is part of the HTTP protocol, and that is a piece of server software that serves information based on requests. We requested a certain web page, it served us a response, and the response was this HTML document. That make sense? Okay. So, we should be able to recreate that actually out here, unless it auto redirects us, which it might. Probably does actually. Oh. Actually, it did auto redirect us because this is not the page we got. This is an auto redirect to this error thing. Don't type that in. Okay. Well, whatever. You got to get what I'm talking about. So this is a piece of software that we would call a server. Now, we know that software is running on a computer somewhere, right? Do we know that that's the only piece of software running on a computer? On that computer? No, they might have a bunch of other servers. Piece of server software running on it. So a physical server may have multiple pieces of server software running on it. And each of those pieces of software can listen on a different port. So for instance, web servers typically are listening on port 80. That's the default HTTP port. Okay, so when you type in www.google.com in your web browser here, it's the same thing as typing in www.google.com:80. Talk to port 80. Oh, come on. Come on.
443 HTTPS.
Here, let me go back to HTTP then. Thank you. There we go. Okay? And notice it redirected to your HTTPS page. The point is, we're talking to the same port. The web browser knows how to talk to web servers, so it defaults to port 80 because that's the port it's usually on. Sometimes if you set up your own web server locally to test something, it puts it on a special port. Sometimes it's port 8080. That's a kind of a common test port, because it's just 80, then another 80, kind of just double up. But you can run servers on any port that you'd like. Okay, and at some point in here, we're going to write our own little server software, and we're going to see how we can have incoming socket connections, kind of like an incoming phone call, and accept that connection and respond to it. That's a server. All right, so you might have a single piece of server hardware with one piece of server software running on it, or no pieces of server software running on it. For instance, we have that Mac Pro down there, which we can call server hardware. Yeah, I don't believe we're running any server software on it that we put on there. I think there's probably a couple default server software that's running on all of our computers. For instance, some of you have file sharing turned on. So file sharing would be a piece of server software. It's waiting for somebody to request files from your shared folder. That kind of stuff. Make sense? Okay? So the perception of a server can mean several different things. Now, when we deal with memory, servers tend to have more memory, correct? Why? Why do servers have to have more memory? We already talked about what memory does. Memory is for short-term storage of pieces of information. Hello. Why do servers typically have more memory? I say typically because it's become kind of a hobby. I've been making fun of it over the last week about people who just have ridiculous amounts of RAM in their computers. But typically servers have more RAM. Why? The more RAM means the more temporary things you can store. Simple as that, correct? Why do servers, whether you think let's think about it as a server, as a piece of hardware that's running one or more pieces of server software. Okay? Why do servers, or why might they need more RAM? Why would they need to remember more stuff temporarily than a single user computer? Hint, hint.
Because they have more than one user.
More than one user. So if we go to google.com, we're not waiting in some line, right? If all of us typed in www.google.com on our laptops right now and we just did a countdown to press enter, we all pressed it at the exact same time, as close as possible at least, we'd all get a response. That server is set up to handle multiple incoming connections. And how does it do that? It does that through something called threads. Now, keep in mind, in the early days of operating systems, the idea of having one program run, having more than one program run on a local computer at a time, didn't work. How could we have one program, a single program, run multiple times for multiple incoming connections at the same time? That was an impossibility. This didn't exist back then. So we have something called a thread, which we'll talk more about. We'll talk about the evolution of that when we talk about inter-process communication. But what happens is, as soon as one of our requests comes into google.com, it spawns off this little worker bee, thread. And it hands off that phone call, that socket connection, and that thread deals with you. While this guy's waiting for the phone to ring again. This happens, let's call it nearly instantaneously. So, request comes in, spawn off a thread, keep listening. Another request, spawn off a thread, keep listening. And it can do that a whole bunch of times. Okay? Is that why servers probably also have more processor cores than your typical standalone computer? It's because they can handle more stuff simultaneously. Many servers are actually designed to load balance. So when we think about Google's web server, chances are this is not one computer sitting in the corner of a room. More than likely with Google, this is an array of computers. I don't know how many. Could be hundreds. Potentially could be hundreds of computers. But I guarantee it's more than one. Okay? So let's just call it many computers. And those computers are involved in something called load balancing. So when the request comes in, those requests are routed to the computers that are least busy right now. And each of those computers are running the same server software, and they can handle your request. Because a single core can handle exactly one request at a time. Now, cores are very, very, very fast. 4, right? There's 4 varies.
I think so, yeah.
Yeah, got it. Zero count. Tricked you. All right, so, although that kind of just supported what he was saying earlier. So you're wrong. You're wrong so that I can be right. So, though each of those cores is very fast, so we can give the illusion of doing more than one thing at a time. Right? Okay? So, memory on a server, the reason we have to have more memory on a server, or the likelihood of needing more memory on a server, is because we have more than one user. And more than one user is like, since each of those users is requesting stuff, we're going to have to temporarily store aspects of that request while we're working on it in that local computer's RAM, in its memory. And we might have 500 people simultaneously using that computer, taking up memory, as opposed to our situation in here with these laptops, where only one of us is using the computer at a time. Make sense? You know, we put far less of a burden on our RAM, on our personal computers, single user computers, than a server computer might have put on it. Even though they're really the same hardware, same stuff like that, there's just a different focus. Server software, or server operating systems, kind of getting back to the core question. What's an operating system again? If you had to concisely define what an operating system is, what might you say? Go ahead.
The main application that handles all the other applications.
Okay. Anything else?
The in-between between users and hardware.
Yeah, it's probably the cleanest answer. It's a piece of software that sits between the end user and the hardware so that it can launch all the other applications, so that it makes it an easy user experience for the end user, blah, blah, blah. When we're dealing with an operating system, I know the actual kernel is the real operating system, but let's just generically say, when we're dealing with an operating system like Windows and the Mac OS, how user-friendly do those operating systems need to be? Very. Because we have a wide range of users, end users using those operating systems. Now, when we talk about server operating systems, so an example might be Linux or Unix. And sure, there's a Mac OS server, there's a Windows server as well that are going to be more user-friendly. But how important is the user-friendliness of a server operating system? Significantly less important, right? Because the people who are directly using those servers, managing them, those kind of things, the IT professionals, they are a technical class of user, correct? They're not sitting there checking their email and stuff like that on the server, generally speaking. Okay? The server has a purpose, and that's to serve data to a group of users. Those operating systems have a different goal. And now, there is a minimalistic goal of being user-friendly. That is, we don't want to be dealing with switches, twisting vacuum tubes, flipping switches, whatever it is. We don't like dealing directly with hardware, but we don't need it to be super pretty. In fact, many times, server administrators, so for instance, let's take here on campus, the main server admin here would be Mark Newhouse, right? So he's having to manage many servers on campus at one time. And here I'll throw in a quick plug. So if any of you have ever been video gamers or something like that, had to deal with Mark and been upset that he won't do what you need him to do and stuff like that, some of you are IT majors, correct? Okay, remember something. Being an IT manager is a thankless job. I know Mark well, he's a good guy. He only hears stuff when it's not working. He only hears about it when it's not working. And he has to balance several things. Network security versus end user happiness. And end user happiness has to also do with network security, right? When you're trying to get your latest, greatest Xbox game to work, you care more about the game working than you do about the security breach that might be, opened as a result of what he needs to do. Concordia it's a weird animal. When you're a university, you have different groups of users that you have to protect. For instance, we have servers on campus that keep student grades, student records, tax documents, things like that. These need to be protected. So the next time you get mad at the IT people, you can still get mad at them. I realize it's always what's in it for me, right? But just remind yourself kind of the types of problems they have to deal with on a daily basis. Lately we've been having a lot of internet outages, right? And our initial gut feeling is, oh, these people don't know what they're doing. There might be some truth to that. I don't know. I really can't answer that question. There might be somebody who's in charge of something who is incompetent. But typically, when you're under an attack, some denial of service attack or something like that, which has been our problem recently, the people who are attacking you are also smart people. So it's almost like a war, trying to figure out how do we best protect ourselves from this when your exterior walls are just getting bombarded. Kind of make sense? So for those of you who are IT majors, you're going to get thrown into the situation. You're going to have users who hate you as well. Okay? So as, try to have a Christian perspective maybe on this. Okay? Check that Christian worldview. But like I said, I know Mark well. And actually, him and I have butt heads on many things, many times. Probably more often than we get along, actually. But he's trying to do a very good job. And sometimes that's not compatible with the end user's happiness. So just kind of keep that in mind when you try to at least understand from their perspective. IT is a thankless job. And we can attach that to many different things. If you want to take the political spin on it, we're all more than willing to complain about politicians and stuff like that. When they're doing their job, no problem. But yeah, things are hitting the fan or whatever, and then this guy's he's just he's breaking all these rules. He's corrupt. Blah blah blah. They probably are corrupt. Okay, but these guys are solving very difficult problems. Doesn't matter which side of the aisle they're on. So I don't know. Not something I'd ever want to do. Because I kind of just like flying under the radar and just doing my own thing. If I mess up, nobody really gets affected except you guys. You're not important. Wait, I got your tuition. Okay, so in any case, understand that server management from an IT perspective is difficult. And the reason that these pieces of equipment have more memory and more processors and stuff like that is they're solving a more difficult problem. The software that the professional is using is the operating system software. It doesn't have to be as end user friendly because the end user is a technical person. And where I was getting at with Mark Newhouse here on campus we have several servers, right? I don't know our exact organization. Some of you who maybe work for IT are going to know more about it than me, but I'm certainly aware that we have several different physical computers that are solving different problems here on campus. We have some database servers, we have the server for Banner, we have the server for Angel, and some of these have different network security stuff surrounding them, blah, blah, blah. Well, more often than not, Mark isn't going into some server room with a couple of monitors and a keyboard plugged in and working directly with the servers. He's sitting in his office and remoting into these servers. And most of the time when you're remoting into the server as a network professional, you'd rather be looking at a screen like this, where you can do command line stuff to move documents around and edit configuration files and that kind of stuff, rather than using a graphical interface, which typically is more sluggish. If you've ever used LogMeIn or something like that to remote into a computer, sometimes it's okay, it solves its purpose, but it does tend to be sluggish because it's loading images, right? So from a network administrator's perspective, sometimes this is the better end user experience. Make sense? All right, we'll pick up from there on Monday. I was going to give you an assignment because I was late. I'll let you off the hook for the weekend. I do apologize. I will not make a habit of that.